Ever since I was a little kid, I've been fascinated by how objects are built and how that relates to their function and application in everyday life. Armed with my set of Legos, a great deal of creativity, and an endless source of imagination, I was able to build anything I could possibly think of. I used to spend hours upon hours carefully piecing together various parts until I was able to create that masterpiece I had envisioned in my mind. Here I am now, 13 plus years later, and that aspect of me still has not changed. Obviously, I don't spend all my free time playing with Legos, but I am constantly using my creativity to think of ways to improve the everyday structures and objects I see around me. I consider how I might make them more cost-efficient, more user-friendly, more innovative. Hi, my name is Nithya Kitabarpu, and my field of study this year in ISM is Biomedical Engineering. So when I first chose this as my field of study, I truly did not know that much about it. Since biomedical engineering is a relatively new subset within the branch of engineering, most colleges and universities have only recently incorporated it into their curriculum. As a result, biomedical engineering is still in its growth and development phase. So, what exactly is biomedical engineering? Well, it's the application of engineering principles to solve medical problems and advance medical care. And if you're thinking right now that that definition sounds extremely vague, you're absolutely correct. Biomedical engineering serves to merge the gap between being a doctor and treating and diagnosing patients to being an engineer who's working in industry and design. As a result, biomedical engineers need to be equipped with a vast array of skills in order to successfully complete their job. There are several different subfields within biomedical engineering. One, for example, is medical imaging. As the name suggests, this is all about the technologies used to diagnose patients and examine patients more closely. One example would be an X-ray. Now, when you take an X-ray, you want to make sure that the image you're translating onto your computer is an accurate depiction of what that patient looks like on the inside. You want to make sure the pixels are quality and that it accurately represents what actually is going on at that site in order to accurately diagnose your patient and figure out what the problem is and solve it. Another field within biomedical engineering is nanotechnology. Now, nanotechnology is all about small devices that you can place inside your body in order to accomplish many of the same tasks that you can do with devices outside the body. One example is a pacemaker. The materials used within a pacemaker and the technology incorporated within it have all been strictly engineered to maximize their efficiency and reduce irritability for the patients. The types of materials you use, you don't want them to be biodegradable. They should not break down within the body, because if they do so, you could be potentially harming your patient instead of helping them. Another subfield that I was actually very interested in the beginning was tissue engineering. Now, tissue engineering is using a foundation of cells to provide a scaffold and then build an entirely new artificial organ simply from these cells. Now, the problem with tissue engineering is that it's really difficult in order to get all these cells to grow together in the proper manner and fashion so that the ensuing organ is functionable. Most scientists have only been able to replicate less complex organs like the liver or pieces of your bone in your trachea. I actually read an article about scientists who were trying to find the proper procedure for rebuilding a heart. And one of the many problems they faced was the fact that there are so many different types of cells within the heart, and there's so many different aspects to a heart because it has to pump your blood and has to be strong enough in order to do so. As a result, they're still unable to find that perfect procedure that accurately accomplishes their function but doesn't hurt the patient they want to put the heart into. If they are able to accomplish this and build an artificial heart, however, the possibilities are truly endless for this piece of technology, because if you're able to recreate a heart, the necessity for transplant lists would extremely reduce. For example, transplants for hearts, many patients are on the waiting list, and they're on the list for very long times, such as years. However, if you have the ability to build artificial organs, for example, such as hearts, you wouldn't have the need to have such long waiting lists, because you'd be able to take cells from that individual, put them onto a scaffold, apply the necessary treatments to it, and then build this artificial organ specifically for that patient. So blood types wouldn't be a problem. However, out of all of these subfields I listed above, the one that I really, really felt passionate about was prosthetics and biomechanics. What really interests me about this field is that you're creating devices that need to be able to effectively interact with the human muscle system, the skeletal system, and the nervous system. These three systems determine our motion, how well we can move, how well we are able to interact with the world around us. Therefore, if you need a prosthesis which serves to either support or replace missing organs or body parts, this prosthesis needs to be able to replicate a human hand or a human leg, which brings about the question, how accurately can these parts be replicated? Take, for example, your arm. It might not look like much, but there are so many different types of nerves and muscle systems working together just so I can close my fist or open my hand. As a result, whenever a prosthetist is trying to replace a body part and give it to their patient in order to be functional, they have to consider so many different things as they're building that. As I thought through this and I started really focusing in on prosthetics and biomechanics, I knew that there was still a lot more within the field of biomedical engineering that I could potentially pursue. Therefore, because the next phase of the ISEM program was to conduct research interviews, I decided that within my research interviews, I wouldn't singularly focus on prosthetics, but I would branch out and test other fields as well. Because who knows, what if I liked another one better in application? My first research interview was with Professor Heather Hayenga, who teaches at the University of Texas at Dallas. Now, Professor Hayenga specializes in the use of cardiovascular imagery in research. What she does is she's built a computer program, and she works very closely with a clinic at the school. Patients from the clinic have their data incorporated into this program, and this program is able to predict future levels of risk for a cardiovascular disease and how degenerative that disease would be. This is extremely important because if you have a patient who has about a 65% chance of getting a disease within the next 5 years, you want to hold off on treatment until it's absolutely necessary, because insurance doesn't start paying in until you're within the 85% risk range, which really shocked me. I did not know that. Another interview that I had was with Dr. Searcy, and he serves to research in the field of image-guided drug delivery. He basically is focusing in on cancers. How do we effectively design drugs that target cancer cells without harming the cells around them? But the most important interview of them all was the one that I had with my mentor, Mr. David Wilson. Now, Mr. Wilson works at the University of Texas Southwestern, and what he does is he's a prosthetist and orthestist. And what that means is he works both with patients and with actually building these very devices I was talking about before. What's really fascinating to me is I didn't know that you were able to do both parts of this job. See a patient, diagnose what that patient needs, and then build whatever that patient needs. So that was really interesting to me. And after I'd gone on all my 6 research interviews, I contacted Mr. Wilson requesting that he be my mentor for this year, and he accepted. One of my first mentor visits that I remember was him teaching me about the process of building a prosthetic device. Obviously, it's going to be a lot more complicated than what I can accurately define because I still have a lot more to learn. But the basics are this. First, you start with casting your patient. And what that means is you take plaster bandages, and I'm going to talk about lower limbs here. You would wrap it around the patient's leg. In doing so, you wait for them to harden, and once they've hardened, you have a cast to use that you can then modify. When you modify them, you want to mark the bony areas and the soft